So on your worksheet 7B, they give you an original function at the top, and then it gives you 6 transformations of that particular function, graphed, but also written in function notation below it. So your job is to match it up, and there's not going to be any leftovers, like there's 6 of each. So did we already do number 1? And we decided that one was a pretty easy one. That was just shifted down, and we had to count. But if we look at our choices, there's only one that was shifted down 5 units, or down any units, and that would be choice F. And then I think we got 2 matched up, didn't we? We saw clearly that there was a reflection, but we noticed if you look at the original and like you reflect this guy back up here, wherever it lands, that's not where it shows up over here on this function that's graphed. And the same thing here, this guy's down here, but then it got shifted back up. So we're looking for something that had a reflection with a vertical shift, and that would be this guy, A. And that's where we left off. So number 3, I can tell by just the shape of the graph that it's been vertically stretched. So look at your choices. There's only one that's been vertically stretched. Do you see it? A vertical stretch would look like a coefficient in front of the function. Would it be choice D? Yeah. And since that's the only one with a vertical stretch, I don't really have to count and make sure it's a stretch of 3. I'm sure it is. Oh, this is that weird one. So they took the negative parts of your function, these guys, and they took the absolute values of them, so they flipped them up to the positive part, and that was the absolute value of the function, so that's choice E. And then let's see. Comparing these two, I can definitely tell there's some sort of reflection going on, but it appears to be reflected across the y-axis this time, so that's like a horizontal reflection. So horizontal reflections are the newer ones for you guys. That's where they throw a negative into the function. So that would look like choice B, f of negative x. And then, are we almost done? Well, there's one left, so let's see if it matches up. Oh my gosh, pen. There we go. I definitely see a reflection, and I think that's all I see. So is there one that just has a vertical reflection? Yeah, choice C. Got a good. All right, if you could please now, in your notes, find worksheet 8 from your notes packet. We have to talk about graphing piecewise today, and then we're also going to talk about how to write piecewise functions from a graph. So basically, we're going to learn a lesson and then do everything we just did in reverse. Now, this first question here, this is just to get you thinking about what a piecewise function looks like and how you can evaluate them. But this is also really good practice for a question that's coming up on your test next week. So this is not in your packet anywhere, just a little warm-up. It says, evaluate this piecewise function at x equals -1 and x equals 4. So this piecewise function is the line 2x plus 1 if your x's are less than or equal to 2. And then it switches to the parabola x squared minus 4 if your x's are greater than 2. So when they first asked me to evaluate at x equals -1, so if I plug in -1, I got to choose which piece of the piecewise function it is defined at. So -1 would be all within the domain of less than 2. So using that blue function, 2 times -1 plus 1 is -1. And then going back to the piecewise function, this time trying to evaluate it at x equals 4. Well, 4 is greater than 2, so you're looking at the parabola piece this time. So what, we have 4 squared minus 4, so it would be a 12. So if the question was just to simply evaluate the piecewise function, you have to be very careful which piece of the function you're looking at. However, if I change the question to say, is this continuous at x equals -1? In order for this function to be continuous, both of your pieces, or all of the pieces of the piecewise function from the left and the right side of -1 have to match up. So we just found out that if you use the left function, the blue guy, plugging in -1, you get -1. But even though it's not defined at the green piece, you still have to plug it in there. So if you take -1, square it, and subtract 4, you get 1 minus 4, which is -3. Are we getting the same output value here? -1 versus a -3? No, we are not. So is it continuous at -1? No. that's the kind of continuity question you might experience on your next test. Now, that's a piecewise function. You could graph it, and you'll see if there's a jump. Do you guys remember what it looks like on a piecewise function if they do match up at the same point? So like instead of the lines kind of having this big jump discontinuity between them, they overlap at the boundary line and they connect. So that's what it'll look like if it's continuous. Obviously a discontinuity is really easy to see because there's a big gap in the graph. All right, back to your notes now, guys. You're looking at worksheet 8. And if you have colored pens, highlighters, that sort of stuff, I would be using them today. And for sure I'd be using a pencil for the graphing components. But colored pens and highlighters work great. If you don't have a highlighter or anything like that, I got some yellow, green markers all over the place. I'm going to be using highlighters plus 3 additional colors. So if you have like an Office Depot sitting in your bag, go ahead and get it out. Is Office Depot still open? I don't even know. Is that the... No, Office Max is the one that's closing, right? Oh, yeah. So, you've talked about how to graph piecewise before when you were in Algebra 2, but your piecewise functions in Algebra 2 were pretty stinking boring. All the pieces were linear, and usually there's just 2 pieces, maybe 3 pieces if they got crazy. So it was real basic piecewise functions. In PreCalc, like, we're better than that. So we're going to have nonlinear pieces. We're going to have quadratic pieces, square root pieces, sometimes cubic pieces. But we're not going to make them real crazy. But I just want you guys to understand, like, you have to have a really good view of what the graph is supposed to look like before you go play connect the dots, because they're not going to be lines anymore all the time. So this piecewise function, the first piece of the piecewise function is the parabola 3x squared. But it only exists for x's that are less than -1. The next piece of your piecewise function is what we call a constant function, and that's between x's of -1 and 4. And then the final piece of this piecewise function, I think I covered it up, but there's a 3 right there. It's a cubic graph that's been shifted to the right 5 and up 2. So we'll come back to what the graphs are supposed to look like in a moment. What I want you to do first is if you have a highlighter, I want you to mark up what I call the boundary lines. So the boundary lines are any place where the function switches. I'm seeing -1 and 4. -1. And this is not a part of the graph. It's just kind of a visual cue for me. Oops, that's not -1. Try again. Like I said, -1. Your hat. I keep thinking someone has their hand in the air because out of the corner of my eye I see like you can keep it on. And then at 4 there's going to be another switch. Alright, here we go. So this blue function, it's supposed to be the quadratic 3x squared. And if you want to give yourself a little sketch, you can, but it's one of those parabolas that, whoops, the vertex, oh geez, that's ugly. So the vertex is at 0, 0, but it's been vertically stretched by 3, so it's going to be real skinny. So I'm going to kind of keep that in mind when I go to graph this. But what I like to do on piecewise functions is I start at whatever their boundary line component is, and then I get some points after that on the correct side of the boundary line. So, for instance, -1. I know it has just a less than symbol, so whenever I find the point at -1, it's not going to really exist. So I'm going to draw a little open circle to remind me. And if I plug in x equals -1 into the function, so 3 times -1 squared, you get 3. So I'm going to draw an open circle at -1, 3. So it's kind of a piece of the parabola. Not quite. Now for this blue function, it exists for all your x's that are smaller or to the left of -1. So I need to get a couple more ordered pairs, at least one more, where I can get a picture of the parabola, a little more so. So just give me any number that you want that is less than -1, but please don't go too far. Like, can we go -2? Can we get crazy? Alright, so let's plug in a -2 for x into that blue function. So -2 squared is 4. 4 times 3 is 12. See, already I'm off the graph. So let's plot an actual point this time at -2. Let's pretend 12 is up here. And I can kind of visualize for myself what this parabola would have looked like had I drawn in the whole thing. But you guys are only allowed to draw this side of it. So Oh man, that was like the worst parabola ever. Okay, so that was supposed to be curvy looking. I failed big time. Here's what I don't want from you. Better picture than that would be good. What I don't want you to do is in Algebra 2, you guys were taught just to like connect the dots and make a ray. These aren't going to be rays every time. So if it's supposed to be a parabola curve, make it curvy. Do a little better than I did. That was really ugly. All right, this green part though, these are my favorite. These constant functions, and I crossed off half of the line. Is it -1 right there? Okay. So between -1 and 4, so in this section here, you have a constant function at -1. So you just draw a little horizontal line here at -1. And the only thing you have to watch out for are whether you have open circles or closed circles on each of the endpoints for the boundary lines. So right here, it does equal -1, so you're going to put a closed circle. I kind of missed. Oops. And then on 4, I noticed that green function is not defined at 4, so give me an open circle right there. Make your open circles really gigantically exaggerated, especially if you're using pencil on a coordinate plane, because it's hard to see. Okay, one more piece of the piecewise function. This guy is a cubic graph, but we said it was shifted right 5 and up 2. So cubic, the parent function looks like this, wiggles through the origin. So if I think about shifting it right 5 and up 2, it's going to look something like this. Whoops. Oh, man. Where that wiggle point is at 5, 2. We'll come back to that in a moment. Let's go ahead and figure out what happens at x equals 4, because that's going to be the first point that I can actually plot on this red function. It does say equal to 4, so it's going to be an actual ordered pair. Could you please plug in a 4 for me? So 4 minus 5 is -1. -1 to the third power is still -1. So -1 plus 2 is 1. So at 4, 1, give me a good old ordered pair. And we just kind of determined a minute ago that this weird, I don't know what to call it, it's not the vertex, but it's like the center of your cubic function, was shifted right 5 and up 2. So I'm going to go ahead and plot that. But what I don't want to see is you guys connect the dots and make an array. This is not an array. This is a cubic function. So let's get one more ordered pair just for fun. Let's get the ordered pair x equals 6. If I plug in a 6 here, I get 6 minus 5, so 1. 1 to the third power is 1. 1 plus 2 is 3. And again, you're looking at that going, Abruzzo, it looks like a line. It's only a line if you make it a line, guys. These are curvy. So this guy is one of these, and then it kind of starts swooping down, but then it gets cut off because the domain stops. Now, Hofbauer in her lesson, if you want to watch that later, if you don't like this lesson, what she does is she has them go through with a pencil and draws the entire function, like the whole thing, and then she comes back and erases the part she doesn't want. I'm not organized enough to do that, and I'm lazy. So I try to do the least amount of work as possible. So this is why I use this method. But I really like her method too, especially if you're like, oh boy, I don't know what this function is supposed to look like. Now guys, never forget, you have a graphing calculator. So if you're not really sure what x minus 5 to the third power plus 2 is supposed to look like, type it into y1 and get a picture of it. All right, this one, is this on your notes? Awesome. All right, let's get this one done. So you have 2 boundary lines this time. I notice you're going to have a switch at 0 and also at 2, so let's mark that up. That's why I use highlighters, because if you have to go on the axes, it's kind of hard to see. So there are 3 planes on that picture. There's this left part, there's this teeny part in the middle, and then there's this right part. So we're going to be graphing our 3 pieces of our function. We're going to start with our old friend x minus 5. Guys, that's just a line. That's a line with a slope of 1 and a y-intercept at -5, excuse me. So we're going to be able to graph this really well, but you have to be careful with piecewise functions that you're only graphing the part of the function that you need. So at 0, we're going to have an actual ordered pair because it says equal to. Go ahead and plug in a 0. Well, this isn't a shock. It comes out to -5. We already knew that. So at 0, -5. That's going to be a point on that blue function. Now, you're only allowed to graph numbers for this part that are less than 0 for your domain. So give me your favorite number that's less than 0. Negative what? Negative 1. You guys are so creative. All right, so if you plug in a negative 1, you get negative 1 minus 5, so negative 6. So at negative 1, negative 6, you have your next ordered pair that you can use. And guys, we just discussed this is a line, so in this case, you can play connect the dots if you want to think of it that way. But you are graphing the ray because it's only half of the, or part of that line. All right, this middle function is the parent function, that cubic graph, which remember it looks like this, kind of. So that's the shape I'm aiming for. Because this one has not been translated at all, it's supposed to go through the origin. However, I notice that we're between the domain of 0 to 2, so this little skinny piece here. So I'm supposed to have an ordered pair. However, do you guys see it's not equal to at 0? So instead of 0, 0 being a point, you guys are going to draw me a very exaggerated open circle at 0, 0. And then what I like to do, and you can come up with a couple different ordered pairs here, guys, because it's not a line. It's going to be curvy. So if you plug in a 1, you get 1. And if you plug in a 2, you get 8. Now, we're on the next boundary line. I'm allowed to use x equals 2, so I'm going to go ahead and close that point up. All right, here you go. Draw. Oh, I missed. Okay. I went a little too far over. But the idea is it's part of that cubic function. It's just that little piece there. Now, to someone just walking in the door right now, they might think I just drew part of a parabola. So when we get to the next part of the lesson where you guys have to write me functions, there's technically more than one answer to all of the things that were assigned. So if you get a different function than what I intended it to be, you still might be okay. But I'll give you a warning on your homework. Like, I chose really basic functions, so don't get creative, I guess is the message. All right, guys, we got one more piece of the piecewise function. Maybe you don't remember what this looks like. Maybe you have no clue. That's okay. Can you go to y equals, and can you graph 2 divided by x in y1? You should get something that looks like this. Let me know if I'm wrong, though. So that is, it's called a couple different things. Some people call it the reciprocal function. We call it the rational function. It is a rational function in PreCalc. And they have lots of asymptotes in them. We'll learn all about them, in a couple of months. But because we're restricting the domain, I'm not going to graph all of these things, both these branches. I'm just going to graph part of it. So starting at x equals 2, I don't actually have a point there. So I'm going to use an open circle when I get there. Can you please figure out what happens when you plug in x equals 2 to that function? If my pen will work, I'll write it down. All right, so at x equals 2, you get 2 divided by 2, better known as 1. So at 2, 1, open circle. Now, I can tell from my little sketch and your calculator work that we're going to be graphing this little tail piece here. So give me another couple ordered pairs and we'll be in business. So like if you choose x equals 3 or x equals 4, you get decimals, and that's okay. This is like 0.67, and this is 0.5. So, I don't know. I can't draw very well, so who am I kidding? But it does that little swoop down thing, and it creates that horizontal asymptote at the x-axis. The important thing that we understand today, though, guys, is these are not simple Algebra 2 piecewise functions. They are not going to be linear on all the pieces. That's the most common mistake here, is you guys just connect the dots and hope for the best. You got to make sure you understand the underlying function. All right, this next one, let's get our boundary lines graphed with our highlighters. I got a -5 and a 2. Okay, so I see the 3 domain components. Let's start graphing. So, I'm hoping from memory you guys can think about what this looks like. This is x minus 6 quantity squared, so it's a parabola who's been shifted how? Left 6, very good. So that blue guy is going to be one of these parabolas. and his vertex is going to be over here at negative 6, 0. So let's kind of explore on the domain starting at the boundary line. So on negative 5, I don't exist. So I'm going to put an open circle when I get there. What do you get when you plug in a negative 5 here? Let's see. Negative 5 plus 6 is 1. 1 squared is 1. So at negative 5, 1, open circle. But everything before that, you can go ahead and graph for me. So let's get, hey, don't we know negative 6, 0 being the vertex? Let's get one more ordered pair. Let's go negative 7. When you plug in negative 7, negative 7 plus 6 is negative 1. Negative 1 squared is 1. So when you don't have a linear function piece, I suggest you do more than 2 ordered pairs. I would do a couple of ordered pairs. A couple more ordered pairs. So I would do like 3, 4 even. But remember, you guys told me this was a parabola shifted to the left 6, so make sure that what you're about to graph looks like that. But it's not the whole parabola, it's just part of it. I nailed that. Look at that. That's good. Go me. Alright, this next piece, it's like a little vacation. It's just a nice constant function at 7 between x equals negative 5 and x equals 2. So up here at 7, you got a constant piece. And I notice it's got an equal to bar for both endpoints, so you have closed circles on both endpoints. And then, this one you probably aren't really sure what's going on. There's some weird algebra tricks happening here. Those of you who are curious, you could factor out a negative as a separate coefficient and taking the absolute value of it. So when you go to graph this on your calculator, it actually looks like an absolute value graph that's been shifted right 4 units, which is what it is. So it's one of these when you graph it on your calculator. By the way, does anyone remember how to find absolute value bars on your calculator? What menu it's in? Math, and then you go to where it says numerical, and it's the very first one. It says ABS. So if you ever are in a situation where you're not really sure what it looks like, you can get an absolute value bar set in the math menu. But let's go ahead and figure out what's happening at x equals 2. I know it doesn't really exist, but do it anyways. Plugging in a 2. 4 minus 2 is 2. Absolute value of 2, still a 2. So 2, 2. Give me an open circle. We just kind of discovered that this absolute value bar, his vertex is going to be at 4, 0. And, you know, just for fun, let's get an ordered pair over on this side a little more. Let's go x equals 6. You can choose any x you want as long as it's on the right part of the domain. So 4 minus 6 is negative 2, but it's the absolute value of negative 2. So that comes out as 2 as well. And with those 3 points, I think I have enough of it to create a picture. Oh, that's beautiful. I'm going to frame that. Look at that. You're not impressed? Come on, guys. Think about what my graphs really look like. It's pretty good for me. Okay. Oh boy. I'm kind of bored with graphing. Mind if we move to the next part of the lesson? All the graphs are kind of the same, guys. So on the worksheet that you picked up, there's a single worksheet that has this title on it. Those are technically notes. We had some last minute addition to your notes. And then the packet you guys picked up, that's going to be a large chunk of your homework that you're going to work on the next 2 days for work days. But I really like this part of the lesson because it's what we just did, but in reverse. So I'm going to give you the graph, and you're going to come back and find the function. So a little bit of warning before we get going through these problems. We didn't get super creative when we came up with these questions. So they're either going to be linear, or constant, or a parabola, or the square root function. We'll talk about that when we get there. So don't go looking for some extra fun functions out there in the world. Just stick to those main ones. The other thing I want to warn you about is we really didn't mess with the a values. So like remember when you throw a 3 in front of a parabola, it makes it skinnier. And if you vertical stretch, you know, if you throw a 1/2, it makes it wider because that vertical compression. We didn't do that to you on this part of the lesson because that's actually really hard to find. Do you guys remember the test question last week where you had to like find the ordered pairs and then go find A? Like that'd be a lot of work. So we're really nice to you on this worksheet and the subsequent homework where you don't have to mess with A values. All you guys need to know is identify what kind of function I have and then has it been shifted, right, left, up, down, possibly reflected across the x-axis. All right, so here's what I would do. if you have colors, use them. This first piece starts here, ends here, with an open circle, and that's going to be, I always go in the same order every time. I always do the left piece first. And then you have another piece. This guy, I'm going to call him the red piece. It's going to be my next function. And then the computer program we used for these, they don't like to use arrows for some reason. So go ahead and add an arrow to your picture on that third piece. And if you'd like, you can go ahead and highlight the boundary lines, but this is kind of weird. This guy has a whole bunch of boundary lines. He's got one there, and he's got like this weird thing here. And then he like hops over here, and then he like stops here too. So if I had my life to live over again, I would have wished that these coordinate planes had numbers on them, because my old lady eyes, I can't see the blocks very well. So can you guys help me count when it comes to that part? So this first blue function, whoops, that's not what I wanted. We're going to come back to the actual function itself. I would like you to set up the domain restrictions with me before we get to the function. This blue function exists between, let's see, 1, 2, 3, 4, is that -5 and -1. So in order to write that as a sandwiched inequality, you say if x is between -5 and -1. So -5 less than or equal to x, which is less than -1. That's how you write between -5 and 1. Did you notice though I used equal to on the -5, but I did not use one on the 1. Why is that? Look at the circles. Yep, ordered pair, open circle. So this red piece, be careful, he hops over a little bit. He starts at x equals 1 and then goes to x equals, oh my gosh, I can't count. 1, 2, 3, 4. So we're going to say if x is between 1 with a closed circle and 4 also with a closed circle. And then this last green piece picks up again at 4, but it doesn't have a circle. It has an open circle. So x is greater than 4. I think that's actually the hardest part of the question, coming up with those domain, how you write the domain restrictions. All right. Man, it's like your birthday on this blue piece. That's an easy function, guys. That's just a constant function. You just got to figure out where it is. Is that at -2? Now this green piece is also very easy to come up with. That's also a constant function, but where is it? I don't know if I counted right. Let's see, we're all saying different things. You guys can't count either. Let's see. 1, 2, 3, 4. I got 5 for the green piece. The origin's right here. All right, now the red piece, you got to think a little bit, guys. I can clearly see that's a line. So if I can come up with, so you guys are looking at me weird, is it not 5? I don't have my bifocals on, so. Oh, yeah, this is 0, so 1, 2, 3, 4, 5. 5. I'm going with 5. Okay. All right. This red piece is clearly a line. So if I can figure out his slope and his y-intercept, then I'll have my line equation. That's the easiest way to come up with it. So I think I can figure out both of those things with a little muscle. Let's figure out slope first. You have to be able to determine where two ordered pairs are located, and this is kind of hard on these graphs because they look a little weird. So just go to the endpoints. So it rises 1, 2, 3, 4, 5, 6, and then it runs to the right 1, 2, 3. So your slope on that red piece is up 6, right 3, better known as 2. Now, the other thing you got to figure out for me, guys, is if you can anticipate where it would have crossed the y-axis, because I need that as well. So you can either backwards do your slope, or some of you can just visualize that super well. Can you tell where it would have crossed the y-axis if it existed there? Is that -4? So lines just take a little bit of muscle because you got to find the two pieces and then place them down. I know he didn't actually exist at -4, but if he did, then he would have been at -4. Oh boy, here we go. Your first piece is not linear, it is a parabola. We'll come back to that. I'm not going to draw the boundary lines in. My pictures are getting too messy. The middle piece here is going to be a little line. Not too worried about that. I can even see the y-intercept. And then this last piece is another line. And let's go ahead and assume that there's an arrow at the end of it. Alright. So, we'll come back to developing the functions in a second. Let's do the domain restrictions. So I promise you, none of these weird functions, so the parabolas, square roots, whatever you're into, none of them have vertical stretches. So the only thing you have to anticipate is whether you have a right or left shift, and an up or a down shift, and whether you maybe are reflected. So this parabola, I can see his origin, or his vertex, excuse me, is not on the origin anymore. He's shifted 1, 2, 3, 4 units to the left. So, oh, I said I was going to do the restrictions first, didn't I? Come back to that in a minute. Okay, right here, guys. This blue guy exists when x is less than -2, but it's also equal, isn't it? Less than or equal to -2? Because it has a filled-in circle there at -2. This red piece is going to be between -2 and +2, but both of them have open circles. And then this green piece picks up again at 2 and goes greater than 2, but this time it's a closed circle. So when x is greater than or equal to 2. All right. So now back to that talk about our parabola. This parabola has clearly been shifted left 4. What does that look like in a function for a parabola? X plus 4 quantity squared. Very good. So this red piece, clearly it's a line. If you can tell me your slope and your y-intercept, we're in business. So for slope, I'm going to count up 2, right 4. So what is the slope of a line that goes up 2 and right 4? Be a positive 1/2, I heard. Thank you. And you can actually see where it crosses the y-axis right there. Where is that? Wow. 3. Beautiful. Okay, your green line. This is a little tricky because my picture is really messed up right now. But let's just assume on a test I would give you ordered pairs to look at for sure. Let's assume this is an ordered pair and this is an ordered pair. Can y'all count slope with me? It's moving down 1, 2, 3, 4, 5, 6. 1, 2, 3. So your green slope went down 6 and right 3. What's that slope? -2. Good. Now, you do have to figure out where it crossed the x-axis, so you kind of have to backtrack here, guys. If your slope is -2/1, you can also move up to left 1 a couple of times. And that would have been where the y-intercept should have been, which is at what value? I think it's 10. Can someone confirm that? Okay, good. So it's up at 10. There you go. It's not too bad. I really do think like this part is probably the hardest part for kids, because you just got to be careful about, is there an open circle, is there a closed circle? They're not easy, guys. I'm not going to pretend like this is an easy thing we're doing. All right, 3 pieces here. I don't know why I'm messing with my colors. This first piece I'll call the blue piece. Oh man. Now, this third piece, we haven't run into him today yet. Anybody remember what function that is? Yes, the parent function to this is the square root of x. Now, he is not centered at the origin, so it's been transformed somehow. We'll talk about that in a minute. Whew. All right. This has been an exercise in visual for Mrs. Abruzzo today. I don't think I can count very well. So can you guys help me with where that blue function begins and ends for his domain? How far over is this part? -7? We're going with that? Okay, -7 to -3. So I notice closed circle on -7, open circle on -3. So between -7 with a closed circle to 3 with an open circle. Thank you. -3, you said. And then the red function, I can handle that. That's -1 to 2. There's a closed circle on -1. There's an open circle on 2. And then this cute green square root function starts at 2, but it goes greater without, it doesn't have a point at 2, so it's x is greater than 2. Oh, goodness. All right, guys, I love that blue function. That's nice. It's constant. What is it? 1, 2, 3. Is it 4? Okay. And then the red one is a line, so we should be able to count slope. 1, 2, 3 over 1, 2, 3. So your slope on the red line went up 3, right 3, so the slope is 3. And I think you can see the y-intercept if you look carefully. It starts at up 2 on the y-axis. Yes, what I screw up? One. Gosh. You should say. That was really dumb. I'm sorry. 1. Like I said, 1. Because 3 over 3 is not 3. Good point. All right, thank you. X plus 2. And then this green function here, you guys told me it's like the parent function of him is the square root of x, but I can tell it's not starting at 0, 0. It's been shifted. How? To the right 2. So what does that look like for a function? X minus 2 in the body of the function right there. Yep. Ta-da! All right. Whew. What's the next one look like? You know what? Oh, that one's actually kind of fun. I was going to skip it, but I don't want to. All right, so, boy, here we go. Blue function. There's an arrow on this last function. Okay. So I promise you guys, the only types of functions that I'm going to give you, linear, constant, quadratic, and square root. So that first piece, everyone was kind of like, what the heck is that? It's supposed to be a square root graph. So, let's see. Blue guy, 1, 2, 3, 4, 5. So from -5 with an open circle to -1. Oh my gosh, you forgot your inequality, Abruzzo. Less than -1. Red guy goes from -1 to 2 with closed circles on both. And then the green guy goes from x is greater than 2, and there's an open circle on it, so no equal to on that guy. Okay, assuming Abruzzo didn't do anything weird to you on this question, let's assume this is the start of our square root function. So how far over did that get shifted? 1, 2, 3. Is it left 5? So as a function, that looks like this, square root of x plus 5. And then this line, this is pretty easy, right? If I can count the right way this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. So your slope is up 9, right 3, so our slope is 3. Look at me reducing and everything. All right, and then your y-intercept, I can clearly see it crosses at a positive 1. Boom. What's going on with this guy? Let's assume that's the vertex of a parabola. So he's been shifted right to up 4, but he's upside down. So that means there's also a vertical reflection. So right 2 would be x minus 2 quantity squared, and then up 4 would be plus 4. Woo, that was a lot of transformations put into one problem. That's fun. All right, lesson done. You guys are going to tell me which questions you want me to cover in a video that I'm going to post for you later.